Okay, so we're going to look at a new type of differential equation called homogeneous differential equations. So that's of this form here. If dy by dx is a function of y over x, then we call this a homogeneous differential equation. So we can solve this if we use this substitution here, y equals v times x. Because if we do that, then we can make it into a separable differential equation. So let's look at how we can do that. So if y equals v times x, and to be clear, v is also a function of x, then we'll differentiate y with respect to x. So that means dy by dx equals dv by dx. So we take the differential of the first, just using the product rule, times x, plus the first function times the differential of the second function, which is x. Differentiate x, we get 1. So we end up with that. So that means we can write dy by dx, as we said, as f is a function of y over x. And if we just substitute in y equals vx, then instead of writing f as a function of y over x, like that, we will write it as f, and y is vx, so vx over x. So now we have dv by dx times x plus v, and you'll notice the x's will cancel in that f is a function of vx over x. So what are we left with? We are left with, I'll write it over here, dv by dx times x plus v is equal to a function, f is a function of v. So that means dv by dx is equal to f of v minus v, just rearranging this equation, and divide by x. And now it is a separable differential equation, because this implies then that 1 over f of v minus v dv by dx is equal to 1 over x, and then we can integrate we've already separated the variables, okay, and then we can substitute back at the end. So let's look at the example that is from your book. So let's just scroll down a bit, we've got some space. So the first question, or the example, says if we've got dy by dx, and that is equal to x plus 2y over x, well, we need to show it's homogeneous, and then we need to solve for y in terms of x. So currently, we can't separate the variables, we can't use any of the techniques we've learned so far. So we need to use this substitution, y equals vx, and solve from there. So step 1, to show its differential equation, we need to show that, what do we need to show? We need to show that dy by dx is some function of y over x. So if we simplify this, we've got a common denominator, so x over x is just 1, and then we get plus 2y over x. So therefore, we're left with this y over x, got a constant here. So now dy by dx is a function of y over x, therefore we can solve by using this substitution. I'll write it in red here, y equals v times x. Okay, so using the product rule, let's just do one step at a time. Then we get dy by dx is equal to dv by dx times x plus v. Okay, so now we can compare with the differential equation. So we've got this substitution, y equals vx. So that means y over x, which I highlighted in yellow just before here, is equal to v. So now we get, let's write out the next step. So this is dy dx, okay? And then the right-hand side of the equation was this part here. So this must be equal to 1 plus 2v. Okay, because if y equals vx, that means y over x equals v. And I've put this value of y over x, which is v, from there and made it v. Okay, so now we can separate the variables. Let's go about doing that. Okay, so what have we got? We've got dv by dx times x plus v equals 1 plus 2v. Therefore, we're going to get x, I'll write it all like this so it's nice and clear, times dv dx equals 1 plus v, just subtracting v from both sides. So now we can separate the variables. So if I divide both sides by x and both sides by 1 plus v, that means we get 1 over 1 plus v, dv dx is equal to 1 over x. Now we can use our integral sign here. Let's just scroll down a bit. So what does that mean? That implies then that the integral of 1 over 1 plus v dv is equal to the integral of 1 over x dx. And using our knowledge of integration, we're going to get ln 1 plus v. Make sure you use the absolute value signs here. It's equal to ln, absolute value of x, plus c. And just to make our calculations easier, we generally let c equal ln absolute value of a, which is still just some constant number. So we get this ln absolute value of x plus ln absolute value of a. Using the rules of logs, we're going to get ln a times x is equal to ln absolute value 1 plus v. So obviously the things inside the brackets must be equal. So we get 1 plus v, or I'll just write it as v plus 1. That's what your book does. So v plus 1 is equal to ax. And we want everything in terms of y, because that's what the question was. So v was equal to y over x. So now we get y over x plus 1 is equal to a times x times through by x. So this implies then that y plus x equals ax squared. And just making y the subject, we get y equals ax squared minus x. Okay, and a is just some constant number. Right, so that is the first part. So that's the general solution. We've solved for y in terms of x. Now we want for the second part, it says we want a particular solution when y equals 3 over 2 and x is equal to 3. So once we've got this general solution here, the next parts should be quite straightforward in general. Basically, we're just substituting the values in and some basic algebra. Okay, but we'll just go through it for this example. So let's just scroll down so we've got some space. So we've got 3 over 2, so that's our y, is equal to x squared, so that's going to be 3 squared and then minus 3. So therefore we get 3 over 2 is equal to 9a minus 3. And then if we add 3 to both sides, then we're going to get 9a is equal to 9 over 2. So let's just write that out. So I'll write on the side 9a is equal to 9 over 2. So therefore a is equal to 1 over 2. Okay, so that's essentially how we do the homogeneous differential equations. And I think there's about 5 questions of this exercise, of these exercises in your book. So it's a good idea probably to do all of those questions, because it is very good practice, and it can be a bit of a challenge just to get used to doing the substitution of y over x is equal to v, what does v equal, what does y equal in terms of v, and all those sort of things. Okay, so that is homogeneous differential equations.